So we have already seen the syntax and semantics of the propositional logic. So syntax is what defines what sentences look like, and semantics defines what makes them true. Propositional logic provides a foundation for reasoning, okay? Simple but powerful enough for the Wumpus world type of problem. So now we will use this system to talk about entailment and inference. That means if the knowledge base is true, we derive some truth from that. We make sure that we can derive a sentence which is also true, that which is called entailment. We have seen it before. How to derive new truths from existing knowledge, that's entailment, okay? But we need to use inferencing and in different rules for that. So now we can, to determine entailment, we have two different ways. One is model checking, which is by examining all possible models and verifying that a sentence holds true in every one of them. That method works, but it can be slow because there can be many propositions and hence exponentially many models. So you can see if there are three literals A, B, and C, then there will be 2 to the power 3 equal to 8 models. Okay, so this is basically exponential, right? So that's why there is another way, because the model checking, the agent enumerates every possible combination of truth values, every word, to see if the knowledge base entails a sentence. We try to see another approach which is called theorem proving, where we instead use symbolic reasoning, okay? Manipulating logical statements directly through valid inference rules. There comes the concept of inference rules or logical equivalences. So then you understand the difference between the two methods, right? One is model checking, another theorem proving. Model checking enumerates all possible methods, models, but theorem proving only applies inference rules to derive truth. The efficiency of model checking is exponential, but for theorem proving approach, it's often linear or polynomial, okay? Like model checking is basically a brute force truth table based approach, where you create truth table, all possible combinations, and then find in which the knowledge base is true, and then you entail the given sentence. But for theorem proving, it's just a symbolic proof chain. Theorem proving is often much faster, okay, when the number of models is huge, but the proof chain is short. So so what is a logical equivalence? So logical equivalence are, when two sentences alpha and beta are said to be logically equivalent if they are true in exactly the same models, okay? So something like, let's say, this is the left side of this picture is about logical equivalence, okay? So this side is logical equivalence. Let's see if I can use a pen. So this is about logical equivalence, okay? So how it works, so P and Q is equivalent to Q and P. So this is called commutativity, or alpha and beta is equivalent to beta and alpha. So commutativity of the AND operation. Similarly, alpha or beta is also equivalent to beta or alpha, which is commutativity of the OR operation. Now we can have associativity like alpha and beta within parentheses, and then gamma, it can be spread around like this, alpha and beta and gamma, which is associativity. Similarly for OR. So double negation operation. So this is one thing. Then we can have alpha implies beta. We have already talked about implication before, and we said that the implication is a important concept where we are trying to determine that P implies Q is true in all cases except when P is true and Q is false, right? Like for example, we said that if 5 is even, then Sam is smart. Since 5 is not even, this statement is considered true, okay? This entire statement is considered true because we never violated the rule. 5 is not even, so Sam is smart. The 5 is even, Sam is smart, this entire statement is true, okay? It might sound a little bit strange, but remember, P implies Q does not mean P causes Q. Just means whenever P is true, Q must also be true. Okay. With only one case it will be false, when Q is P is true but Q is false. Otherwise, it will be true for everything. Anyway, so now let's go back and see that alpha implies beta. There is a very famous rule or logical equivalence called contraposition. Alpha implies beta can be converted to not beta implies not alpha. We'll see the uses of this when we apply them in the Oompas word problem. Alpha implies beta equivalence to not alpha or beta. This is implication elimination. Okay, implication elimination. So now we have alpha biconditional beta is basically, I've already shown that alpha implies beta and beta implies alpha. It's called biconditional elimination. Now we can have De Morgan's law, which says not of alpha and beta. When you open this parenthesis, it's not alpha or not beta. It's De Morgan's law. Also, if it's in the or format, not of alpha or beta, it will become not alpha and not beta when you open the parenthesis. Include or bring the negation sign inside. So the distributivity is another one where alpha and beta or gamma is, we are basically multiplying alpha and beta or alpha and gamma. Okay, that's what here distributive. Now if you distribute over the or, then this will be alpha or beta and this and alpha or gamma. Okay, so this one distributivity. Now these are all the logical equivalences. There are a few more. Okay, sometimes it's called on inference rules also. So before that, we want to tell that a key concept of this theorem proving is validity. Okay, because the theorem proving approach we want to apply is called validity. A sentence is valid if it's true in all models. So meaning it's a tautology. Okay, like this is a form and this is also a form. So the if it's true, then this will also be true. It's a corresponding tautology. Okay, so like P or not P is always true. So no matter what the value of P. So if alpha is valid, it implies, or it biconditional alpha is true in every model. Okay, so we can define the entailment in a new way according to the deduction theorem. So alpha entails beta if and only if alpha, so like let's say alpha entails beta, if and only if, which is also written as IFF, alpha implies beta is valid, like alpha implies beta is valid. That's a concept of validity. Okay, valid. Okay, this is the concept of validity. So checking if one sentence entails another becomes a question of proving that an implication is always true. So whether entails or not, we just need to prove whether this is implies or not, its implication is true. Okay, which is exactly what theorem proving tries to do. The theorem proving method is trying to do that. If you try to see beta, alpha entails beta, we just have to show alpha implies beta in all possible models, always true. So there are a few other rules. Modus Ponens, which is P implies Q. So this is implies that sign. Okay, so this is using single arrow, not a double arrow, but this implies that. So if P implies Q, P is given. This is comma P. So this is also written as P implies Q and P is given. So that means Q is true. P is given means P is true, already known. So that means Q is also true. So this is the meaning of that. Okay, it can be written like this also, corresponding tautology. Modus Ponens is another rule which says if P implies Q and Q is known to be false, that means P is also false. Hypothetical syllogism is P implies Q and Q implies R, so P implies R. So it's like transitivity. Simplification, P and Q means P. Okay. because both are true. It's conjunction, right? Simplification. So conjunction is P comma Q can be written as P and Q. I mean, both P and Q are true. You can write it P and Q. Disjunctive syllogism, P or Q, not P. That means Q has to be true. Okay, P or Q. That means either of them have to be true for this expression to be true. And we already know that P is not true, so Q must be true. Addition is something like, let's say, P means that P or Q I can write. P is true, then I can write P or Q with another literal Q, irrespective of Q is true or not. So let's stop here and see how can we apply them to to the Wumpa solve problem.